Hey everyone, welcome back, and today let's solve Leetcode problem 38, titled Count and Say. So the count and say sequence is a sequence of digits strings defined by the recursive formula. To be completely honest, this is quite confusing, especially at first. Let's go ahead and see how this really works. So count at say with the parameter of 1, or starting with 1, is simply just a string 1. And count at say, well, for any n, is going to be the run length encoding of count and say n minus 1. And now, what run length encoding or RLE really is, it also gives us like a Wikipedia formula. Let's not worry about that right now. Basically, it's a string compression method that works by replacing consecutive identical characters that are repeated 2 or more times to actually be consecutive with the concatenation of the character and the number marking the count of the characters, basically the length of the run. Now, I'm not going to lie, the first time I read that, it didn't really make any sense. Let's go ahead and really look at the examples that they provide us to understand what they really mean. So, for example, if we wanted to compress the string 3, 3, 2, 2, 2, 5, 1, we can replace that 3, 3 with 2 3s. And we can replace that 2, 2, 2 with 3 2s. And we can replace the 5 with 1 5 and the 1 with 1 1. Hopefully this makes sense. In 3 3 3, notice how these two 3s are actually consecutive. So instead of having 3 3, we know we have 2 3s. And so we'll put the count of the number of 3s in front and then the actual value itself, kind of why the problem is called count and say. Here we have 3 consecutive 2s. We know we have a count of 3 2s, and so we're going to put the number of 2s that we have consecutively right now here, 3, and then the actual value that repeats, so 2s. This basically means 3 2s. And then we replace the 5 with 1 5. Why? Because we only have one singular 5, and so we have a count of 1 or 1 5. And then we replace the 1 for the same reason. We have a singular or 1 1. And that the compressed string would then become 2 3 3 2 1 5 1 1, following that run length encoding or compression method formula. So we're given a positive integer n, and we want to return the nth element of the count and say sequence. So in example 1, we have n to be equal to 4, and our output would then be 1 2 1 1, because count at say with the parameter of 4 gives us the output of 1 2 1 1. And so let's kind of recursively or just generally see how that works. Now we're automatically given that count at say of 1 is guaranteed to be the string 1. Now count at say at 2 would be the RLE of 1, so it would be 1 1, because we are guaranteed that count at say at n is the run length encoding or the compression formula or result of count at say at n minus 1. We know count at say at 1 is 1, and so count at say at 2 would be count at say of 1, so it'd be 1 1. Count at say at 3 would be 2 1s. Why? Because we have 2 1s in 2. Count at say at 4 would be basically whatever 3 is, and so it would be 1 2 and then 2 1s, or in other words 1 2 and then 2 1s, or 1 1, right? So that's the reason why we have for 4 count and say to be 1 2 1 1. So as you can see, this is a recursive problem in nature of how we actually try to solve the problem. In example 2, we actually have the base case or the initial starting value n to be 1, and we're already guaranteed that we start off with count and say of 1 to be 1. There's nothing to build off or continue from here. It's just the base case, and so we're going to have an output of 1. So for the constraints here, we are actually given that n is going to be within 1 and 30. Very small constraints, and that kind of was expected because we are going to have a relatively slow approach in recursion, which isn't known to be the fastest of algorithms, and so it is pretty good, and hinting for these smaller input constraints that this is actually a recursive problem, right? So now let's go ahead and get into the main observation that we really need to make to really solve this problem. And that is, each term is really just generated by counting the consecutive digits in the previous term. It's kind of like that recursive and compressed method or formula nature. And that means that our solution also needs to iteratively build each term based on the one before it. Because again, count at say sub n or at n is going to be the RLE of count at say of n minus 1. We're going to build each term based on the term before it and applying that count and say compression or run length encoding formula, right? So really to solve this problem efficiently, again, like we just talked about, we're going to be using that iterative approach, I don't know how to pronounce that. And the reason why, again, is because each term is going to depend on the previous term. And so we're going to kind of build off iteration by iteration, or term by term, up until we get to the nth term, right? So we're going to start with the base case. That's going to be sequence to be equaling 1. And then we're going to iterate from 2 up until n, whatever that value input is, to actually construct each term iteratively. And for each of those terms, we're going to first read the previous term character, basically character by character, and then we're going to actually count the consecutive digits and construct that new term by appending the count and the digit to a string. That's kind of like our compression method. And then we're going to continue this process iteration by iteration for all values, building it off of the previous one until we actually reach n to be our input, right? So now let's go ahead and see how that actually is implemented in code. So like we just talked about, let's first actually initialize our base case here. Sorry about that. I have some code from an old problem, right? So let's get our initial sequence. And it's going to be initialized to the simple string of 1. In fact, I'll use double quotes. I think it's a little bit neater, at least for me to kind of visualize, right? Step 1, or rather, sequence 1 is going to be our base case, because we're always guaranteed that the first term is always going to be 1. That's the term that we build off from. And now let's actually begin iterating through and generating terms iteratively from or up until our input n, so from 2 to n. Right? We've already generated the first term, and so we have to actually iterate n minus 1 times to generate the next terms up until n. So in the range, let's just have an underscore as my placeholder for my iterator. So we're going to iterate this number of times in the range from n minus 1. The reason why we have n minus 1 and not n is because we've already generated the first term, and so we're going to have one term less than n, right? So for every single value or term in this range up until the nth term in this count and say function or method, right? We're going to get the new sequence. The new sequence is the new sequence that we're building off based on the previous term, right? And it's first going to be initialized to an empty string because, of course, we haven't actually built anything in the current new iteration yet. And we're also going to get our count to initially be initialized to 1. Now, this new sequence string is actually going to be helping us build the next term for this current iteration. And this counter, I just called it count, is actually going to track the consecutive digits to apply that compression method, right, if you will, right? So now, in this for loop here, we're going to have another for loop here, and that's actually going to iterate through the length of the current sequence, right? Basically, the previous term that we have to build off from to get our next term, the actual compression method kind of for loop here. So let's iterate through the previous term, or the current sequence. So for I in the range, starting from 1, going up until the length of our sequence. I really hope that's how you spell sequence. Looks to be right. Basically, here we're just iterating through the sequence starting from index 1. Why do we start from index 1? Because we're actually comparing each character from the previous one. So if we start from index 0, we'd get an index out of bounds error because we can't have negative indices when we're actually comparing. And so just to not worry about that, we're going to start from index 1 in the current sequence. Right now, in the current sequence, if sequence at the current index I, so I'm just going to say if sequence at I, looks like I forgot it at C, sorry about that. If the current value in the sequence, if it's equal to the previous value, sequence at index I minus 1, we know they're going to be consecutive values because they're equal, they're adjacent, and they're equal. And so we're going to have to actually compress the string. So we'll increment the count by 1. That's the count for the current kind of list of consecutive occurrences, right? That means the current digit matches the previous one. We have to increment the count for these digits because we are actually counting the number of these consecutive occurrences. However, if this isn't the case, meaning these current adjacent digits aren't actually equal, they aren't actually the same, that means we don't even have to compress them, and so we can actually just get our new sequence. That's basically going to be, it's going to be a little bit Pythonic, but I'll explain how this works. It's going to be the string of the current count plus the sequence at I minus 1. Now, why are we really doing this? Well, if the current digit is different, or it differs from the previous one, if we fall into this else conditional, we simply have to append the count in terms of a string plus or followed by the previous digit to the new sequence, because that's exactly what the problem statement tells us. We want the count, and then we want to actually get the digit that appeared that number of times, or count number of times, right? So we'll get that new sequence, and then we have to actually reset our count back to be 1 because we just found the most recent sequence, and so we're going to have to restart our count to be 1 to build off the next sequences, right? We have to actually reset it to be 1 for the new digit. Now, once we actually get that out of the way and actually iterate through to build the next sequence, let's actually build our new sequence for the next iteration as a whole in the outer loop here, and it's going to be basically the string of count plus sequence at -1. Right? Sequence at -1 is basically going to be our most recent sequence that we just built, and effectively after actually exiting this for loop here, and this inner for loop here is what I really mean. we have to actually add the last counted sequence because the loop is only going to process these changes, right? Now, once we actually get the new sequence and add that last counted sequence, let's get our sequence and update it to be the new sequence because, of course, this is the new sequence that we have to then build off of from in the next iteration. So we can actually process it in the next iteration. So we're updating the previous old sequence to be the new sequence. And effectively, we're returning the final sequence because this would actually contain the nth term of the sequence once we actually finish all these iterations in n-1, right? So if I were to submit this, unless I made any syntax errors here, this should be accepted and there should be a valid solution. Let's go ahead and see if this works. I may have made a very simple syntax error here, but as you can see, this really is just about as efficient as you can get it to be. So on a high-level rundown, how does this solution actually work? Basically, we're first starting our sequence or initializing with the base case or base sequence of just the string 1. That's what we kind of build off from. And then in these for loops here, we're actually iteratively building the next term based on the previous term by actually counting its consecutive digits and compressing it accordingly according to the problem statement, right? And then we have to actually construct the new term as a string by appending the count and its corresponding digits into the current or new sequence, and then updating the new sequence, and then repeating until we actually reach n, so n-1 times, right? And then we have to actually return that final computed sequence, which would actually be the nth term of the most recent sequence that we actually generate. So for the runtime complexity here, this is actually a recursive solution, and so the runtime complexity is going to be big O of 2 to the power of n, or 2 to the n. Why? Because each term is actually going to roughly double in length as n increases, and since we actually iterate through all the terms up until n, we also know that the overall time complexity would also grow exponentially, and so this is actually a big O of 2 to the power of n, or exponential time complexity. And that brings us to the memory complexity, or the space complexity. For a very similar reason, it is also big O of 2 to the n, or 2 to the power of n. It is also exponential. Why? Because we're actually storing the sequence as a string, and we know that's also going to increase in size exponentially with n as our input integer. And so this is also going to be a linear, or rather a exponential memory or space complexity, right? This problem does grow very rapidly, and that's why we don't want large n values. They would give us a TLE. That's why n is at most 30 in the input constraint. So that's why it works very efficiently for these smaller n value inputs. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.